Good morning once again. So this is your second question for the one concept per day portal, and this question is taken from November 2024, the recent one which is passed away. Okay, now let us start with this. The concept here is about binding energy. In the first problem, you have already learned about what is binding energy, and then how do you interpret the binding energy per nucleon curve, and making use of it, how do you prove that the energy released in case of a fusion or in case of a fission is always seen to be positive, or it has been energy is being released in both the cases. And then we have already learned about how do you find out based on the binding energy or based on the half-life, how do you find out what is the activity. A part of the question was already shown. Now let us start with this question. This question is also very unique because it gives you a different perspective of binding energy. Let us look into it. So first question as usual is what is meant by binding energy. Let us write down. So binding energy is nothing but binding energy is the energy required to remove the nucleons or separate. You can also write, instead of remove you can say separate the nucleons from the original nucleus. The original nucleus. You can say something like this. Then calculate in giga electron volt per c square the mass of a nucleus 54Xe131. Okay, this is being given. So calculate in giga electron volt per c square the mass of a nucleus. It is not asking you the binding energy because the binding energy is already given to you. Okay, how do you find from this data? Which means now you see it has 54 protons. Xenon has 54 protons, and how many neutrons? 11 minus 4. I'll use my calculator to get the value of what is this now? 131. 131 minus 54 is 77. So it has 77 neutrons. Okay. So therefore, it has so much number of protons and so much number of neutrons. What is the energy required to separate all of them? It's nothing but so much, 1.105. But you need to find out what is the mass of this nucleus. So how do we find out? So we know that 1 UpC square. 1 UpC square. What is 1 Up? 1 Up. U is the mass of a proton. Okay, that's why I written the suffix P here. 1 UpC square. 1 Up mass of a proton multiplied by C square will be equal to 938 MeV, while 1 UnC square is equal to 940 MeV. The difference between these two is only 2 MeV. That you need to remember this. Okay, this you remember, then the rest of them would be automatically you get this across. The energy released by a neutron or the energy of a neutron is higher than that of an energy of a proton by 2 MeV. That's what you need to know. Okay, so towards it, now if I now let me define this binding energy. Now the binding energy, as we know, is nothing but the energy of the constituents minus the energy of the nucleus. What is the energy of the constituents? Okay, we have to find out. Binding energy is already given to you, 1.10 eV, 1.105 giga electron volt is equal to energy of the constituents. How do you find energy of the constituents? You will write down what are the constituents over here, protons and neutrons. You will write down 54 times then U plus 77 times N multiplied by C square. N I'll write this as Up and you'll write this as UN over here. Okay. So many number of protons multiplied by mass of one proton. So many number of neutrons multiplied by mass of one neutron. This is your energy of the constituents minus energy of the nucleus as a whole. This has a mass M and this is C square. You can write like this over here. Now what is being asked over here? Again read the question. It's in terms of giga electron volt per C square. So what I will do is this C square is common. I'll keep this out downwards. So this I will, or maybe I'll write it here directly here. So what I will do is I will write this as 54 Up. What is 54 Up? 54 into UpC square plus 77 into UnC square minus MC square. I'll write like this over here. Now we know that UpC square, 1 UpC square is 931 MeV. So I'll write this as 54 into 938 MeV plus 77 into 940 MeV minus mc square. What is this now? 1.105 giga. What is giga? 10 power 9. Okay, mega is 10 power 6. So let me convert this also into mega. This is also into mega. So which means I'm going to multiply this by 1000. So which will be 1105 MeV. I'll write like this. All of them are MeV. Okay. Now I need to find out. I need to simplify this. Okay. And what is that I need to show? I need to show in terms of what is the mass of the nucleus. Anyway, let us do this also here. So therefore, if I do this, let me use my calculator. And I'll first take the sum of these products. I take 54 multiplied by 938 plus 77 multiplied by 940. How much is going to be? 1,23,002. This much you get. Minus, what is that on the other side? I have 1105. 1105. When I do this, I get 121927. Okay, so therefore, so I have this mc square goes that side, and this one will come in this direction. So therefore, I will be getting this as mc square is equal to 121927. 121927. What do I need? I need the value of m. Now, what is this now? This is your MeV here. So mass of the nucleus is equal to 121927 MeV divided by c square. I can write like this, or I can now write this as, how can I write this? I can write this as 120, if I convert it into giga, this will become 121.9 giga electron volt divided by c square. This will be the mass of the nucleus. I hope you understood this, right? Okay. Next, let us go on to the next question. Let me just check out the answer. According to the marking scheme, this is 122 giga electron volt. Why is it 122 giga electron volt? Because you see 121.9 is 122. I can now write this as 122 giga electron volt divided by c square. Okay. So xenon 54, 133 and 131 are two isotopes of xenon. Outline what is meant by an isotope. What's an isotope? Isotope is for 2 marks. An isotope, I should write this as, isotopes are elements with same proton number but different neutron number. See, this has 2 marks. We have defined the element over here. We have defined the definition over here. Put the definition over here. This will be for 1. Then the second one, cite the example. Example 54 xenon 133 has F454 xenon 133 has how many number of neutrons? Let us calculate that also. 133 minus 54 will be 79. Thus 79 neutrons, and while 54 xenon 131 has how many number of neutrons? 2 less, 77 neutrons. Okay, but number of protons is equal to 54 in both elements. Okay, and hence they are isotopes. Next, xenon 54 133 is radioactive. 54 133 is radioactive. This is your radioactive. This is radioactive. I'll write this as RO. Suggest how the binding energy per nucleon for 131 xenon compares with that of the 133 xenon. Okay, so compare with the binding energy per nucleon. What is binding energy per nucleon? Tell you actually. Binding energy per nucleon. If binding energy per nucleon is higher, what does it tell you? It tells you it is highly stable. If it is lower, okay, I'll write down binding energy per nucleon is high, then this says it is a highly stable element. And if it is low, it is less stable. When you say xenon is radioactive, 133 is radioactive, but the other one is not radioactive, that means now this will have a low stability. That's the reason why this element xenon 154, 133, 13354 will immediately disintegrate. Okay, maybe its half-life could be 1 year, 10 years, whatever it is, but definitely it is not stable. It disintegrates. While this one, he doesn't say it's radioactive. As a result of it, what can you say now? So this is seen to be stable. I can now say from here that 54 xenon 131 is more stable than 54 xenon 131, right? So because we are looking only at the stability, you cannot comment based on the half-life, you cannot comment based on the number of nucleons, number of nucleus present, number of atoms present in the sample. You cannot do all these things over here. You can only talk about the stability based on the binding energy, because binding energy per nucleon only reflects about the stability. It doesn't tell you anything else. Okay, next, let us move on to the next one. The graph shows the variation with the time of the activity of a pure sample of 54 xenon. Okay, so this is a plot of the mass number along the y-axis and the number of days along the, no, not mass number, sorry, Becquerel. It's activity along the y-axis and number of days, number of time along the x-axis. Estimate the half-life. A very simple question. What is this value of 8? This is 8, and what is this value here? 9 over here. If this is 9, then the activity reduces similar to that of the number of atoms. Okay, for every one half-life, activity reduces by half. So if this is 9, 4.5, where is 4.5? This is 4. This could be 5. 4.5 could be here. Just draw a line parallel to the time axis. It will intersect at this point. Now from here, drop a perpendicular. It will intersect over here. Now let us look at the x-axis here. This is 4. This is 6. This should be 5. This should be 5.5. This should be around 5.4. 5. What I will do is, what is the unit? Days. So I can now say the estimate of the half-life. Because estimate, there is nothing given over here. You can always say some approximate number between this point and this point. So this could be 5.4 days. Then next is, the answer should be between 5.2 and 5.2. Calculate the activity of the sample after 25 days as a fraction of the initial activity. 25 days. Now, I would have been happy if this was 5 days, I can easily calculate. Okay. But since it says about 25 days, now it's not a multiple of this 5.4. Okay, what I meant is that, see, if I have an activity, let me go by the first method. In my previous videos, you would have seen this method. Okay, what I do is I take n naught or activity. After one half-life, okay, it becomes a by 2. After second half-life, it becomes a by 4. Third half-life, it becomes a by 8. Fourth half-life, it becomes a by 16, and so on. I do it like this. So what is this t here? 5.4. If it is 5.4 and 25 days is asked, how much multiple of 5.4 can be 25? This could be 5.4. Then from here to here, it could be 10.8. From here to here, it is 10.8. Like this, if I calculate, this will be another 5.4. So 10.8 plus 5.4 would be 15.8, 16.2. Another 5.4, 16.2, 16.6, 21.6. And then the next one, a by 32. A by 32 here, 16 point, what did they say? 5.4, 10.8, 15.8, 16.2, 16.6, 7, 21.6. The next one would be, once again, if I take 5.4, 21.6, 22 plus 5, 27 days. But I want only for 25 days. It means I am estimating it here. I am estimating it here. I am not estimating at this edge, right? So it will definitely not be a by 32. It will be some other value. So I need to determine this. So I cannot go by this method, okay? Because this value cannot be used over here. Now what I do is, there is one more method. What is that method? That method is a equal to a naught e to the power of minus lambda into t. What is this? This is similar to that of n equal to n naught e power minus lambda. Okay, we already know that activity, number of atoms follows the same rule. So I can use this equation. Now towards it, now what should I do? I should now find out the value of a. What's the value of a naught? A naught value is, what's the value of a naught? At t equal to 0, what was the value of a? A is nothing but 9 into 10 power 7. We already know this. So we will take this value and substitute it over here. 9 into 10 power 7 into e to the power of, what is minus lambda? Minus, what's the value of lambda? We have already found out, 5.4 days. 5.4. multiplied by how many 25 days I have here. Okay, so I'll write this as 25 days multiplied by 20. Okay, so therefore now let us, I need to use the calculator to determine this value. So thus this is 5 point, I'm sorry, this is 5.4, right? It's not 5.4, it will be minus 0.693 divided by 5.4, 5.4, and this multiplied by 25. The reason is because this is not half-life, this is the decay constant. The decay constant is 0.693, which we have already seen, divided by, it should be in per second, but since this is also in days, I put this also in days. Days and days will cancel. Okay, this is days and this is days, this day and this day will cancel. I get this value here. Now let me use my calculator to find out what is this value. So I have, first let us calculate what is there in this region. Okay, so this will now be 0.693 divided by 5.4 is equal to so much multiplied by 25. I get minus 3.2. Let me write it down. It should be 9 into 10 to the power of 7 e to the power of minus 3.2. When I do this, what do I get here? E to the power of minus 3.2 I want. E to the power of minus 3.2. First I will take e power, this e here, where is e here? Do you have an e here? I don't have an e. It's here. E to the power of, there is power here. Power is not there. E to the power of minus 3.21, right? The minus 3.2. I get something like this. I'm sorry, I made a mistake over here. We'll do one thing. First, e power 3.2 will do it. So e is nothing but 2.78. I'll use this one here. X to the power of, e to the power of, e to the caret is there, 3.2. When I do this, I get this one. Then I will take the reciprocal of this. I get this as 0.0407. 0.041. I take this as 9 into 10 power 7 multiplied by 0.041, which will now be equal to this multiplied by 9 will be 0.3668 or 0.37. 0.37 into 10 to the power of plus 7, which should now be 3.7 into 10 to the power of 6 unit is becquerels. Let me check it. What is the final answer? 0.036. So this is what I get. But what is he asking here? He is asking you to find out as a fraction of the initial activity. So therefore, you can now write a by a0. You have to find out a by 0. You need not even do all this over here. A by a0 is equal to e power minus lambda t, okay, which you found out already as e power minus 3.2. E power minus 3.2, which comes out to be around 0.03. You can stop. Okay. So with this, I think we have come to an end to the problems on binding energy. These are the possible types of binding energy that can be asked. Okay. So with this, we come to an end. So hope you have understood the concept on binding energy, how to apply, how to get the value of the activity values, how to interpret the binding energy per unit nucleon, how to calculate what is the energy release. We have seen all this. Thank you for being with me, and if you really like these videos, do share and subscribe to my channel. The more the number of subscribes, likes, it will definitely be an encouragement to me, okay, to keep this channel forever free, and hence it will also help me out to monetize it. Thank you very much.